So hello. So sorry for being late. By late I mean I last uploaded a video almost 3 months back. So actually I was pretty much busy with my coursework here at IMSC. So um, I could not find enough time to make a video on my YouTube channel. So sorry for that. So today I shall be sharing my PhD interview experience at so you so let me check. So as I do in each of my video that I sometimes it has so happened that I have done whole the video and recorded just forgot starting the recording. So it's okay. So today I shall be sharing my PhD interview experience at the IIT Madras. So you all know that IIT Madras has been termed as the one of the best institute in the India. So not one of the best, it is the best institute in India. So it has been by the NIRF ranking or some other ranking. I don't exactly remember the name, so don't accuse me for that. So IIT Madras is one of the best institution in India, and also it does exceptionally well in research too. So I will share the I gave interview for PhD there in physics. So in my case, so let me first write it. IIT Madras. Okay. So I actually what happens in IIT Madras is that in my time they just gave a list of professors with their research interest and the projects they have in their hand. So actually, while applying in IIT Madras, uh, I was not that sure that if I will get selected or not. And the research, they provide the professors and their research topics to let the students decide to which professor they should apply or they should approach. So I just while applying, I just randomly gave two of the professor randomly. I did not, because I did not know any of the research topics that they shared. So I had no idea about the research topic. So I was just confused whom to choose or not, and I was very reluctant that I don't even know if I will get selected or not. So I just randomly choose two of the professors and just filled up the form. So later what happened is that after my interview they asked me, so you want to, actually I was very much interested in theoretical physics. So they asked me in which topic you are interested. I said that theoretical physics. This is all after interview. So then they told me that, so we did not even publish any professor for theoretical research this year. So and whom you have selected, there is no match in your research interest and these professors. So I was pretty much ashamed there, because I just chose them randomly. So that was the problem. So the main thing is that they provide you with the research interest of people and interest and people who willing to take students, and then they call for the interview. So in my interview panel there are mostly there are few senior professors and one or two, around 6 or 7 professors were there. Okay, so mostly senior professors ask most of the questions, and the young professors they ask very little. So one of the senior professors started. So let me share my questions that were asked in the interview. Let's not talk much. So let me just see my note. I have written down the question. So the first question was from, do you know about superconductivity? Superconductivity. TVT. So I said yes, I know. So as I said yes, so they pretty much assumed that I know the basics of superconductivity. So they just asked me a question, that is, say we have a solid superconductor and a hollow superconductor. Okay, hollow superconductor. Here it is 10% hollow, as told by them. 10% hollow, it is solid. These are all are superconductors. Okay, superconductor, conductors. So the question is, how do you differentiate that one is solid and one is hollow? Say their masses is almost same. So mass, density, everything is same. So it's not like that. So say, I mean, you cannot measure by weighting them. Okay. So I mean, I was because if their mass and density is same, then obviously you can tell them it is this one is hollow and this one is solid. So, but the you cannot measure by weighting them. Okay, you have to probe something else. So, and you have been told that these are superconductors. So they first asked me, how do you probe them if it will be hollow and it will be solid. So so I thought a lot, and the only thing that came to my mind, and that should even if you don't know the answer, that is you should immediately know that only one of the most important property superconductor shows is Meissner effect. It is very effect. So what is Meissner effect? It is that is when there is a critical superconducting temperature Tc. You know that. So when temperature of a in a superconducting material, if you lower the temperature very much, around few kelvins, below few kelvins, then what will happen is that if there are magnetic flux inside the superconductor. So let me draw that. So in Meissner effect, say you have a superconductor. If a superconductor, T is greater than Tc. So when T is greater than Tc, then this thing acts as a normal metal. I mean, it is not a no properties observed. So superconductor, so magnetic field line will pass through this. There is a magnetic field here. So it will pass through the superconductor. Okay, but when T is less than Tc, what will happen is that this field line will get expelled from the superconductor. This is very famous picture, you all know, I think. It is in every book you will find. So expelled from superconductor. So this is the property of superconductors. Now because there is zero, B is equal to zero inside. Okay. So now you can say that, I mean, how it is defined from normal metal. In normal metal, what is happening is that in normal metal the flux is constant. If there are some, say B is equal to 2 above Tc, then it will B is equal to 2 below Tc2. It is constant. So B is inside normal, but in superconductor B is exactly 0. Okay, so there are some electromagnetic mathematics of electromagnetic theory that I don't want to go there. But the magnetic field exactly 0 is in superconductor in the superconducting temperature, below superconducting temperature. So this is Meissner effect. So I told them that Meissner effect we can help. So I mean Meissner effect is the only way to probe a superconductor. Okay. Now the next question was how, they said it's okay, right? So how do you probe it is hollow or not? How what tells you that it is hollow or not? So that thing I thought a much, but I could not answer, and I still don't know the answer now. So I would request if anyone of you who is watching this video, if you know and find any answer, please mail me or just drop a comment. Okay. So my mail address is in my comment description. You can mail me there. Sorry, my channel description. So you can mail me there, and just I also want to know this. I mean, and it intuitively thinks that I intuitively think that should be something different in the case of hollow, but I am confused which is right. I have some answers, but I am not firm on this answer, so I cannot tell you that this is the answer. So there is some probability that it should be the answer, but I don't want to say that because I am not sure. So if you know the answer, please let me know. So these are the first question from superconductivity. Then they came to the very ground, down to earth. It is free electron theory, the starting point of solid state physics. Free electron theory. So first of all, they asked me that why free electron theory failed. So failure of free electron theory. So if you know, the free electron theory is given by two people. One is Drude, another is Sommerfeld. Sommerfeld is obviously better than Drude, but not accurate. So what the main difference between Drude and Sommerfeld model is, both are free electron model, but in the Sommerfeld case, he assumed the Fermi-Dirac distribution, which is more reasonable, because Drude model assumed Maxwell-Boltzmann MB distribution. It assumed Fermi-Dirac distribution. It assumed that the electrons obey Fermi-Dirac distribution, and Drude model assumed the electrons obey Maxwell-Boltzmann distribution. That is the main difference between Drude and Sommerfeld free electron model. So, what is the free electron? What is the he did not ask me about free electron model, and everyone should know that, but that's different. What is the backdrop? So, for these things, there is a separate chapter on this thing, the failure of free electron model, in the book Ashcroft Marmin. You can look in that. That is very well explained and written there why free electron model fail. But let me tell you a few reasons for in short. It is one is positive Hall coefficient. So up to in free electron model, the main result of free electron model was explaining the Hall coefficient, the Hall effect, right? So in Hall effect, what free electron model predicts that electron conducts, so the charge of electron should be negative. Okay, so and Hall coefficient should always be negative. But in few metals like aluminium and I don't know, the aluminium I remember, but another I don't remember. Positive Hall coefficient was found. So does that mean that protons conduct there, or any other positive charge conducts there? No. The answer is no. So what happens there? That free electron theory cannot describe. Another is, I should not add it only positive Hall coefficient, Hall effect. It cannot explain Hall effect as a whole. So positive Hall coefficient. Then here this also assumes that Hall coefficient is constant. It does not depend on magnetic field. It does not depend on temperature. Anything. It does not. It says the Hall effect is independent of temperature. Hall coefficient. Hall effect. Hall coefficient is independent of temperature or magnetic field. But this is not exactly the case. The Hall coefficient depends extremely heavily on the magnetic field and temperature. So that thing he also could not explain. So these are the Hall effect thing. That because Hall effect was one of the major benchmark for letting the free electron model gain so popularity. Okay, but so and he could not even explain the Hall effect correctly. So another thing is uh, the famous, you know, probably, that is the CV. Specific it's CV, percent of T cube at low temperature. Actually, it is AT plus BT cube. AT plus BT cube. Okay. So it cannot say anything about this thing, because origin of this thing is lattice vibration, and there is no underlying lattice in free electron theory. It is electron gas actually. So lattice does not play any role, except some. He as there is lattice he has assumed, but that is only, for only collision purpose, not anything. You can assume the lattice to be there is no vibration in the lattice. So lattice does not play any role in the free electron theory. So it is only on the electron gas model actually. So this T cube term does not arise. And even in the AT thing, this AT, it is not actually a good estimate for what is experimentally observed. So this linear dependence in T, it is not experimentally matches the numerical value of it does not matches well with the experimental results. So another thing is, uh, temperature dependent, no, magnetoresistance. Okay, so obviously there is temperature resistance, temperature dependence of the resistance also, but that is secondary. That is magnetoresistance. What is magnetoresistance? So magneto resistance, sorry for bad, sorry for writing it bad. Magnetoresistance, that is, if you in a metal, if you apply a magnetic field, then the resistivity perpendicular to the magnetic field is unaffected by the magnetic field. Okay, so resistance does not depend on magnetic field simply. So it magnetic resistance, but magnetic resistance is the opposite thing. You can guess from the name magneto resistance. So resistance which is related to magnet. So actually magnetic resistance means resistance can be extremely uh, affected by the presence of magnetic field. This is experimentally observed. Whole free electron theory cannot say anything about that. Another one is that Widman-Franz law, that is kappa by sigma t. It is thermal conductivity, and this is electrical conductivity. It is a constant value. This is in high and low temperature region, it is right, but in intermediate temperature it is wrong. So what do you mean by high and low temperature? I will come to the later. So you have to be very careful when you in physics, when you every time you say high or low, you have to be very specific about how much high and how much low. You cannot just say it is high and it is low. So you have to be very specific. So I will come to that later. Okay. So in the intermediate temperature range, it fails. Okay. So there are many failures of the free electron theory that you can find in the book. So I am not going in that details now. So he then asked me that I told about this CV thing. This CV thing. The next question was from the CV thing. The specific heat. AT plus BT cube. So he asked me. You said that okay. So if BT cube term, it cannot be explained by free electron theory, then how it can be explained? So as I told you, it can be explained from lattice vibration, the phonons. Okay, so don't go to phonons, the lattice vibration. Lattice are vibrating. So there are some normal modes that I will come to that they also ask. So they first just ask that this BT cube how it comes, and as I mentioned, high and low temperature region. Or one of the professor caught me and asked me, what do you mean by high and low temperature? What is your low temperature here? I mean, this is always valid at low temperature. Uh, Sorry, low temperature. So what is low? What do you mean by low temperature? Is room temperature low temperature? So exactly not. So by low temperature is by mean. Let me first come to this electronic. This is our electronic contribution. Electronic contribution. It is their lattice contribution. Lattice contribution to specific heat. Okay. This electronic. So you can, by simply looking at this term, you can say that at very low temperature, when temperature is very low, then this term will come into effect, right? Because it is TQ and it is only T. So only at low temperature this will come into effect. And how much low? In the electronic specific heat you can only observe at around T around 1 to 10 Kelvin. Around this temperature you can only observe the specific heat in the electronic specific heat. After that, the T cube term will dominate so much that you cannot observe that. So the specific heat curve looks like this. At very low temperature it is linear, then increases T cube, then at very large temperature it goes as constant. So this thing we don't explain right now, but this is the thing you have to be remembered, that you get T cube here and linear in this region. So in this region it is linear. The okay, so AT, and in this region it is BT cube. Okay, so and this is around 10 Kelvin. And in what range BT cube is valid? So after 10 Kelvin, you can say that BT cube term dominates and T cube terms only it is only T cube dominated. So after 10 Kelvin, you can already neglect this term. It is only T cube, but still we say that it is in low temperature. So uh, I mean, so how much low? So after when we can say that we are not in the low temperature region. So this is given as Debye temperature. So T cube term is always compared with this T. I mean, if theta D is the Debye temperature. Debye, what is Debye temperature? I don't want to go to much details. This is a characteristic temperature for a metal which is around room temperature for most of the metals. Okay, it can, but it is not very less. Okay, so if you know about Fermi temperature TF, it is around 4 Kelvin. Okay, so there are some characteristic time scale. So when we say Debye temperature, it is around 300 to 500 Kelvin. It can also go to 1000 Kelvin for some of the metals. It can also go to 100 Kelvin for some of the metals, but it is not much lower or much greater than room temperature. Okay, so I mean for most of the materials it is around room temperature. So when we say low temperature, we always meet. So for iron. So for iron, the low temperature will be, say, if the theta d for iron is 500 Kelvin, then for low temperature, I mean less than 500 Kelvin. These are low temperature region. Okay, so after up to room temperature, this much thing you can see. To see this much behavior, you have to go very high temperature. So so obviously not in room temperature. This region is very high. This temperature and this is specific heat. So up to room temperature, this T cube term dominates, and only 1 to 10 Kelvin, that is the temperature where the electronic contribution dominates. And why so? Why in low temperature electronic contribution dominates and in high temperature lattice contribution dominates? It is simply reason that is in low temperature the atoms are vibrating less. As what do we know, that if the temperature goes high, the vibration will be higher for the crystal ions. So at high temperature, obviously the lattice will vibrate more, and the dominant contribution will come from this. And in very low temperature, the atoms will vibrate very less, though it will vibrate because of the uncertainty relation, but it will vibrate very less. So the most contribution will come from the electronic specific heat. Okay, so that was the third question. Next easy question they asked, that is what is density? What is density of state, and what is in density of state? And write the expression for dependence of density of state G of E in 1D, 2D, and 3D. So there is a simple formula of the specific heat G of E proportional to e to the power d by s minus 1. Okay, where what is d? D is a dimension, d dimension, and s is if energy is proportional to k to the power s. If energy is proportional to k to the power s, then density of state is proportional to d by s minus 1. So for free electron theory, what do we know? That is E is proportional to k square, h square k square by 2m, you know. So s is equal to 2. So for free electron theory, it will be d by 2 minus 1. So you can put d is equal to 1, 2, and 3 and get the answer. So and this thing you can prove. It's not that I am writing the formula by remembering. You can prove that this formula in general. You have to find the volume of a d-dimensional sphere, then find the number of states per unit volume, and the general procedure for finding the density of states in 3D. You can apply that in d-dimension as well. So that was simple. Then he asked what is device specific heat. So the device specific heat is nothing but that is device. If you read Debye theory, uh, why it is why it is not working? Sorry. Mm. Sorry. I don't know why it is not working. Why my pen is not working. Mm. So it's back. I don't know what happened. So sorry for that. Now it's working. Okay. So okay. So what are yes? So device specific heat. Device specific heat. What is that? It is in the Debye model. What in the you can read the Debye model from the book Astronomy or any book. So in the load in Debye model, what is happening is that we assume omega goes on to something k linearly dependent in k. Okay, what is omega and k? You can read it's simply energy is proportional to k. Okay, you can read like that. Then what is found in the low temperature region specifically is found to be T by theta d cube. So these are device specific heat which says that in low temperature specific heat is proportional to T cube. Okay, so there is a Debye model. The Debye model he asked actually. The main assumption is it is linear in K, which is actually not. The dispersion relation, if you know, it is like this. It is linear in the very vicinity of the it is K and it is omega. And vicinity of K is equal to 0, it is linear, but in this region it is not linear. So what Einstein assumed is that Einstein did assume that it is to be constant. Einstein assumed this thing and found a relation. So both the results by Einstein and Debye just deviate slightly from the exact result, but they assume different things. Okay, so define this is Debye model. Next, I come to the lattice vibration. They come to the lattice vibration. So when you say lattice vibration, we are also uh, this plot. How do we get this plot? So what do you mean by lattice vibration? What is the model that we use? We see that what we do is there are some atoms. We assume we each attach spring to each of them. Okay, sorry, of them and find its normal modes of vibration. Okay, that. So he asked me what is lattice vibration. So I said lattice is vibrating. So he asked me how do you model it. So I told him this model. So and I say that I will find the normal modes of the oscillation of these things. Then he just got on the normal modes thing. So why are you interested in normal? What is normal mode first of all? So I told him the normal modes is that where all the particles uh, oscillates coherently. I mean their phases are fixed. So when their relative phase does not change with time. What do you mean by that? Say there are two particles. Okay, so there are three particles. Say. So what you can do? You can just put three of the particle in the same displacement x, and x. This side, this side, exactly at x. Okay, then leave them. Then what do you say the x1, x2, and x3? Sorry. So what do you expect? That say both of all of them are same. Okay. So what do you expect usually? Usually you expect three of the particles to move or move in it on its own randomly. Okay. You cannot. I mean the position of one particle cannot affect the position of other particle. I mean they are truly independent random. Okay. But it happens that there are few modes. That is, it can so happen that three of the particles. I mean, it would be very much better I could show you an animation. But you can if you can search, if you can find you will find in Google much many animations on normal modes. It is say we have a pendulum. It must easy to so when if so okay, just leave it. Leave the pendulum thing. I think it will be much harder to explain. So, what is happened that three of the particles, they goes they move with same. I mean, if this particle goes this side, this will also go to this side. This will also go to this side at the same time. Or if these go to this side or these go to this side, then it will go to this side also. Okay. So this is called I mean there is some collective motion of the particles, and that motion is very much periodic, or I mean you can say that it very much organized, not random. They all move in a very good, they're all like dancing in some fashion. So there there are some special frequencies in which they can also only if you oscillate them only in that frequencies they will do these things. Okay, so these frequencies are called normal modes. In these modes are called normal modes, normal. So here the phases of the relative phase of the oscillation of the particles is not changing. Okay, so I would suggest you to see a video on what is the normal mode, because a good animation will tell you a lot about how a normal modes work. I don't think I made a good explanation here. So what is happening there in normal? So why you are interested in normal mode? That was the question. So I told him that only in normal mode a wave can propagate, because that we have a fixed value of omega as a function of k. Okay, on if that see you say you want to send sound through a medium. Okay, then what you will do? You will your sound wave will, so these are solid. Okay, your sound wave will hit this, then the atoms will start vibrating, and the wave will propagate through this, and this wave is our phonon or lattice wave, a quantized lattice wave, anything you can name it, phonon. That is okay. So if the all the particles oscillate randomly, if they are not in random normal modes, then the wave cannot propagate. So there are modes which are not normal in the solid also, because it is, but there are many mass molecules, so it is very likely that more much of them will oscillate in normal mode, and they will create a traveling wave there and send the sound in this case. So we are interested in normal modes because only in normal mode of vibration a wave can propagate. So we can get sound can only propagate in that normal mode thing. Okay, so uh, and if you just read the basic theory of monoatomic lattice or dynamic lattice vibration, that is in any standard solid state physics book, you will see that how these waves are formed. You can see mathematically also in, there are good pictures in the books. You can look at them. The main idea is that why, but very I have seen that very few books exactly mention this normal, why normal modes are important, because of this, because they usually think that it is very obvious, but it is not very obvious to me before I knew this. So these are, we are interested in normal modes. I think it is clear. So that's the thing. So then he asked me to write a equation of motion. I draw this thing. So he asked me to write the equation. I mean, what equation of motion you will write? Write the equation of motion for this, and find the normal modes. So you can write the equation of motion for this thing. Like you can So my laptop is hanging. I don't know why. Sorry. So hmm, a lot of problems are coming today. I don't know why. Maybe after a long time I am making a video. So my laptop is also angry on me. Okay, sorry. Uh, so what you can do is just shift this and x1, shift this and x2, and shift this and x3, and I think you can for this one m same, okay, m1. So m1 x1 double dot, the Newton's the law. What forces acting on this? If these are x1, then if it is k1, then k1 x1. Okay, so k1 x1, and you have to be very careful about the positive and negative sign. So I have taken x1 to be positive in this direction. So if our force is in this direction also, or sorry. So if it is in this direction, then the spring will compress and it will move it, and it will get a force in this direction. Sorry. So it will be minus k1 x1. So you have to be very careful in writing this equation of motion. So when again there is also a force in this direction too. So there is a combined effect of x1 and x2 also will be there. It is k2. Then sorry, sometimes k2 into x2 minus x1. This will be the equation of motion for the m1 particle. Okay. Then you can write simultaneously for m2 also, m3 also. Then you can find the normal modes of this equation by the standard procedure is the you can assume it you trial solution form x1 a into the power I omega t. That is a traveling wave solution. So and you can find omega as a function of the system's parameter. So oh, okay. So I have to mention one thing, that is this okay. So I have written is k1. This k and this earlier k is different. This is not this is a wave number. Okay, and this k is a spin constant. Okay, so just be careful on that. So you can find the by assuming this trial solution, you can find the normal modes of oscillation. Okay, so for this case. So for a infinitely large system, there will be k dependence, and you can easily see that. So I will not go into the much into the detail because the derivations are all there in the books. There is no need to repeat that here. Then he asked me about Lennard-Jones potential. I hope you know that Lennard-Jones potential. So, lot of problems today. So Lennard-Jones potential. What is it? It is V of R is equal to minus 1 by r to the power 6, a by r to the power 6 plus b by r to the power 12. Simple. So he just asked me to find the mini equilibrium point. That is very easy. You just make the derivative 0, and then the van der Waals. Then actually one of the professors there, he is working a lot on van der Waals force. So I mean he is probing the van der Waals force in the different types of materials. So he asked me about the different types of van der Waals force. What is van der Waals force? Van der Waals force. So it is simply a weak force, that is the origin of it is due to the uh, say H2 molecule. The if a molecule is polarized, say H2O, okay, HOH. So it is partly negative, it is partly positive. Okay. So if there are another H plus molecule, H molecule here, H plus O minus H. there is a force between acting between them. This is simply the van der Waals force. Okay, that is the force between the dipoles actually. Okay, so in many of the materials, the van der Waals force, though it is very weak, it is very important to keep the materials in same place. So in the what are made most important place is graphene. In graphene, there are some 2D layers which are attracted through van der Waals force. And graphene is a very important material, and a lot of work is going on in graphene. So van der Waals force is acting between the layers there. Okay, but then he said that how then new that you have learned about inert gas, and there is some forces also acting in the inert gas also. No, yes, sir. I say yes. So then, if there is dipole force, then why do inert gas also? So I mean, is there any attraction in the inert gas too? Because in the inert gas also we assume this linear Gen potential. So there is some attractivity is also there. So why this attraction or the repulsion comes in a inert gas? So what I am not sure about the answer, but what I said is there is fluctuation in the dipole moment in a inert atom or something. So a atom, though electrically neutral, there is always a fluctuation. So it's not that charges are equally distant. So in a inert gas, say it's a neon. Okay, so it is a inert atom, so single molecule, but still the atoms are not that it is spherically good, and I mean it is a well balanced. There is well balanced. I mean the charges are uniformly distributed, and that there is no dipole moment. There is always fluctuation in the electrons density, and always like that. So due to this fluctuation in the electron density, charge density around the nucleus, though it will always have a dipole in it. I mean, so and so this fluctuating yes, the fluctuating dipole moment in the inert gas atoms, they are responsible for their interaction. That's what I said. Okay, I'm not sure about it. So that's the thing. So I think he asked me a lot about the van der Waals forces and this thing, but I don't remember all the questions because there are some fine questions also. I mean, fine mean there are more detailed questions, but these are the basic thing, main things that I remember. So next question was what is intrinsic semiconductor? So intrinsic semiconductor, intrinsic semiconductor conductor. What is an intrinsic semiconductor? There is no defect, not defect, and no, by defect I mean there is no impurity or there is no nothing like that. It's a pure silicon or pure germanium. It is intrinsic. Okay. So then he asked me what is Fermi level. So Fermi level is the highest occupied energy level in a semiconductor or in a metal or in anything. Okay. What is Fermi level? Fermi level is the highest occupied energy level, simply. Okay, now in a metal, it is seen that it is between conduction band and valence band. Fermi level is between conduction band and valence band. Okay, sorry, not in a metal. I'm sorry. It is in a semiconductor. It is between conduction band and valence band. Why is that? That's the question. So you can think intuitively like that. Fermi level is the highest occupied energy level. Okay, so in case of a metal, if the highest occupied energy level is this, okay, then if you and in case of metal, what do you know? Conduction band and valence band overlap. So and the highest occupied energy level should be between the conduction and valence band. So it is a Fermi level EF, which is between which is in the conduction band also or in the valence band also. Okay, so electrons can easily go from conduction band to valence band. In case of semiconductor, we know that in semiconductor, its conductivity is not like a conductor. You need some amount of temperature to excite the electrons. So it is only possible when there are gap in the valence band and the conduction band. Okay, it is a valence band is conduction band. Okay, so here Fermi level lies in middle. Now there is a question. I said earlier that Fermi level is the highest occupied uh, energy level of the uh, highest occupied energy level, but you have to that is a different definition in case of a metal. So when you come to semiconductor, you have, because you can clearly see there is no band in the hair. There is no this is a band gap, right? You know it is a band gap. So though we say it is a Fermi level, but actually there is no level exactly here. So how do you define Fermi level for a semiconductor? That is defined from the Fermi-Dirac distribution. That is f of e, probability of finding the electron in a state is given as 1 plus e to the power e minus ef by kbt. So Fermi level is that level where it is half. So when E is equal to F, it is 1 and the probability is half. So this is the definition for a definition of Fermi level for a semiconductor. Okay. So and why it is in the middle? So you can clearly say there is uh, exact actually there is no level in the middle, but as the probability of finding the electron is half there, we say that the Fermi level is in the middle in the semiconductor. Okay, so but the definitions are defined in these two cases. Okay, the definition of Fermi level. Then he asked, "What do you know about chemical potential?" Okay, so now the chemical potential is key. What is, so this EF? You can ask, does this EF change with temperature? Actually not. So EF is actually chemical potential at temperature 0. Okay, so when you are not in the low, when you are at very low temperature, you can always use this formula. But when you are at not low temperature, you have to include the temperature dependence in this EF term, and that is given by mu. So the exact Fermi-Dirac distribution is like 1 by 1 plus e to the power e minus mu at a function of temperature by kBT. So when T is very close to 0 Kelvin, then it is the Fermi level EF. Okay, so usually when we are not at low temperature, then it is chemical potential simply. But yes, what is exactly chemical potential? That thing is different. I mean, in this context, I can say it is chemical potential in a more mathematical way. But physically, what is meant by chemical potential, and how do we change it? How do we do all that things? What is it defined with respect to density? That is a very basic question, and I even do not know much details on that. So I won't go much details in the what is chemical potential or not, because I don't know that much well. So let's not go into that. So this concludes all the questions from IIT Madras. So after all these questions, he asked me, where did you apply except IIT Madras? So I told them that I applied in all these places. So IIT Bombay, IIT Kanpur, these are the IIT I have applied, also in the research institute. So they asked me that how did IIT Bombay or Kanpur conduct their interviews. I told them that they took in the exams and then they took their interviews. So okay, so they are asking a lot about how they conducted these online exams. How was it? I mean, how was the experience or all these things? They asked me. I mean, they also and then they ask that in you want to work in theory, but we have not published any list in theory this year. So have you checked any faculty who is working on the theory group in IIT Madras? So I said, no, sir, I don't even know if I will be. I just frankly told them, I don't even know if I will be selected here or not. Then, what is the point in checking beforehand if who is here or not? So I did not check. so, they did not mind anything. So just said, okay, just check it very quickly, and if who is working in this field, check it. So that was very much a good indication that I will be get selected. That's why they said, if they said that to check the list, because if they were not interested in selecting me, then they would not say these things. And yes, in the result I was selected at the IIT Madras PhD. But though I did not join there, I joined IMSC, as you all know. So, but IIT Madras, I had a very pretty good experience, and it's not about IIT Madras. In almost all the IITs, they test a lot about your basics, and IIT Madras is a good example that you have to be very good at solid state physics. So, IIT Madras is very much good for solid state physics. Then extremely good research is done there in solid state physics. So if you want to work in solid state physics or condensed matter physics, most mainly in experimental part, then IIT Madras is the ultimate point you want to go. Okay, so experimental. There are a lot of facilities in IIT Madras. It is a heaven. Okay, let me write that. Heaven for solid state physics experimental part. Lot of work is going on there. I mean, the people do exceptional work in solid state physics. So, from my interview experience, you can already guess that almost all the questions were from solid state physics. If you don't know solid state physics, it's not almost. Every question was for solid state physics. If you don't know solid state physics, then just forget about getting into IIT Madras. You have to know solid state physics very well. Okay, so and the professors are also good. They will help you a lot, and there are some tips. So okay, so next time when you go for interview in the IIT Madras, be well prepared that you are going to face a lot of questions from solid state physics, and if you know solid state physics very well, you are very welcome. You are welcome to IIT Madras. I mean, they will select you. So I guess I cannot make a stereotype like that, but it is the in general trend. One of my friends also gave interview there, so they are also working in solid state physics, and they do great work. So that is all. So that is